So I asked, like last exam, for some suggestions on what to cover. And I got double the number of emails. That means 2. And so between those 2 emails, they said, we want to talk about 5 questions. So we're just going to try to shoot through those 5 questions. And hopefully that should only take about 25, maybe 30 minutes. And then, of course, I have the exams from the last 2 semesters as well. And we can talk about anything you'd like to after that point. So let's start. So this one is a word problem. Our word problems are going to be shorter in the future. This was back in the day when we had luxurious amounts of time. And there was a story about you're part of an expedition left on Mars. There was an emergency. You were left behind. And you know that the only way you will be able to survive is if you math 265 the heck out of your situation. Now, of course, this was back in the day when we had more salty language and we could use words like heck. We don't put those on exams anymore because that's just too salty for us. Okay. So what's the goal? You need food. And you're the botanist, and so you have some tomato seeds. But you also have some potatoes that you were able to find. They were sent as part of a meal. So you have potatoes and tomatoes. And you're going to make some plants. You happen to have some soil. Okay, so what do we do? Well, the thing is that you don't have a lot. That's what happens when you go to Mars. So you have to use as little water as possible. So we're trying to minimize something. So when you see something as like as little or as much, that's a clue that that's what you're trying to optimize. So we're trying to optimize something. And, well, we have to grow 14 plants. Now that's something, we'll come back to that in just a second. And in particular, if you plant P potato plants and T tomato plants, then the amount of water used will be 3t squared minus 3tp plus p squared. So remember, we're trying to optimize the water. This is a formula for how much water we use. So we can say, all right, we have a function of t and p, namely 3t squared minus 3tp plus p squared. So in some sense, it says if you grow both the crops, there's some sort of combination that reduces the amount of water that you need. But we also have the fact that we need to grow 14 plants, which means that t plus p has to equal 14. Now at this point you say, you know what? I don't need Calc 3. I don't even need calculus to do this problem, because we can do the following. We could solve for, say, t as a function of p, substitute it in. Then we'll get down to a quadratic, which means it's a parabola, and I know how to find the vertex of a parabola using basic algebra. So why do we need calculus? Because it says use the method of Lagrange multipliers, which means we need calculus to solve this problem. Well, no, we don't need it, but if we want points, then we're going to use it. And I think it's a good idea to go into the exam saying, I want points. So I'm going to follow the instructions. Whatever it asks me to find, I'm going to find it. And after that, I'm going to stop, because I'm not going to keep going. I go until I find what I need. Now this t plus p, that's our constraint, because it's t plus p equals a number. So that's my g of t comma p. And our basic mindset when we use the method of Lagrange multipliers is very simple. Gradient of f equals lambda gradient of g. So what you really get is you get a pair of equations. F sub t equals lambda g sub t, and f sub p equals lambda g sub p, which becomes 6t minus 3p has better equal lambda times 1, because g sub t is 1. But I also get that lambda times g sub p, which is 1. So lambda is also better be equal to f sub p, which is minus 3t plus 2p. And if you move stuff around, you'll discover that you get 9 times t had best equal 5 times p. So the number of tomato plants times 9 had better equal the number of potato plants times 5. So when you're doing these types of problems, this happens often, where when you take your set of equations, f sub t equals lambda g sub t, f sub p equals lambda g sub p, and you rearrange them, get rid of the lambdas, you get a relationship in terms of your other variables, t and p. Now the nice thing is, you have another relationship that you get to work with. So let's suppose we solve for t. So we could say that t is 5/9 p, and you plug it back into your constraint. So remember, t plus p is 14, so 5/9 p plus p equals 14. I replace the t by 5/9 p. Well, 5/9 plus 1 makes 14/9 times p had better equal 14, which means that p, lo and behold, should be 9. And t, solve, is 5. And that's what the method of Lagrange multiplier says. We should produce 9 potato plants and 5 tomato plants. And that's where we'd stop. Now, of course, if you were on Mars, you probably have a lot of time on your hands because all you have to watch is reruns of Happy Days. So what do? Well, you say, well, maybe let me just make sure it's a maximum. That's something different. Now, one of the things I didn't explicitly state last time, but I'm going to explicitly state it now, is when you're doing Lagrange multiplier problems, you never, ever use the second partials test. Don't touch it. Don't even think about using it because it's completely bogus. It's not going to give you anything useful. And that applies also if you're doing absolute max and absolute min. If you're doing an absolute max and absolute min problem, never use the second partials test. It's a waste of time because it's not going to give you anything useful. You only use the second partials test when you see the words classify. And if you don't see the words classify, don't pull out the test. Okay, so that's one problem. It's a little bit wordy. So the next ones won't be so bad. Suppose f of xy is a differentiable function, which means I can take derivatives. And I have that g of xy is f of x squared y, xy cubed. And given that the point 1, 1 is given that at the point 1, 1, the tangent plane to g of xy is z equals 7x plus y minus 4, find the tangent plane at 1, 1 to f of xy. And there's a hint. It says, I can think of the following. G of xy I can think of as being a function of two variables, which themselves are functions of two variables. Now, the big clue here of what to do is when you see a function like x squared y inside another function like f. So, function in a function, what's the rule you pull out? It's the chain rule. It's the same as in Calc 1. If you see a function in a function, this is a chain rule problem. Doesn't matter what the functions are, doesn't matter what they give or don't give you, function inside of a function is a chain rule problem. So you need to remember the chain rule. Now the way I like to remember the chain rule is to draw a diagram. So I say, well, okay, I can think of f as really being a function of u and v. So I have f as being functions, say, of u and v, and then v and u, they're both functions of x and y. So I have my chart of dependencies. And I'm going to refer to this chart as I go through the problem. Now, what am I after? So it's good to remember what we're trying to find. In our case, we know what we're trying to find because it explicitly states, in fact, every problem will tell you what it's looking for. We're asked to find a tangent plane. So when you're asked to find a tangent plane, you say, okay, how do I do that? There are sort of two varieties of tangent planes, and remember what they are. Variety number 1, which is the one we're going to use, says that a tangent plane can be found by saying find the function at ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. Now, when do we use this? The answer is we use this whenever we have the form z is in terms of x and y. So I can write z as a function of x and y. So you're saying, okay, well, when wouldn't I use this? Well, I wouldn't use this if I couldn't write z in terms of a function of x and y. So that says that I can't solve for z. Do you remember what to do if you can't solve for z? It's just sort of tangential. Just want to make sure we remember cover our bases. What's the procedure? we're going to use gradient. So the first thing is you shove everything over to one side. You can pick a side, left or right, you decide. It's like Twix, left or right, you decide. But put everything on one side, and then you use the gradient, and that gives you your normal vector. But when you have a function, z as a function of x and y, this is what we're using. So given that we want the tangent plane at 1, 1, that says we need to find the following three pieces of information. What is f of 1, 1? What is f sub x at 1, 1? And what is f sub y at 1, 1? And by the way, this f sub x here just means the derivative with respect to the first slot. And so when we talk about function of x and y, it's just saying x indicates the variable that I associate with my first slot. So the f sub x is the derivative with respect to my first slot. Similarly, f sub y is the derivative with respect to my second slot. So I have to find those three things. So let's go through these in probably order of increasing difficulty. Suppose I wanted to find f at 1, 1. Well, here's some good news. Notice I have the tangent plane to g at 1, 1. And what do I know? I know that g of 1, 1, that's equal to f at 1, 1, because 1 squared times 1 and 1 times 1 cubed is still 1. So I know that's true, but I also know that because the word tangent means to touch, that the tangent plane to g will touch g. So that says if I plug 1 into this tangent plane, so 7 times 1 plus 1 minus 4, that's equal to g of 1, 1. And therefore, the conclusion is that f of 1, 1 has to be 4. Now, how do we do the partial derivatives? Here's where we go through and rely on the trees, the chain rule. So, suppose I want to find g sub x. G sub x. What would that be? Well, if I follow, because remember this is g. This is our g over here. Because g is equal to f of x squared y xy cubed. That would be, according to the rule, f with respect to the first slot times u with respect to x plus f with respect to the second slot times v with respect to y. So what I'm doing here is I'm just going through and saying, where are my x's? How do I get to that? Well, take the derivative of f with respect to u, take the derivative of u with respect to x, take the derivative of f with respect to v, take the derivative of v with respect to x. Now, this is the part where it gets a little teeny tiny bit confusing, and I apologize for this sort of abusive notation, but on a side note, what we have here is when I'm thinking of f as depending on u and v, I have this f sub u, but I could also say, look, f sub u is the same thing as what I'm going to call f sub x later on. It's just referring to the derivative with respect to the first slot. So if later on I'm going to pull out and say, oh, when I said f sub u, it's really f sub x. Okay? That's a slight abusive notation, but I've done worse. Oh, I've done worse. Okay. It should be v sub x. That is correct. Thank you for pointing out my error. V sub x, yes. In fact, we should also go ahead and put down g sub y, f sub u, u sub y. And here's where we have fv, vy. Now, we're going to do this at the point 1, 1. So we plug in 1, 1. So that would be g sub x at 1, 1 is f sub u. And now we say, well, what do we get when we plug in 1, 1? Well, we get 1, 1 times u sub x. Well, let's look at u. What is u sub x? U sub x is 2xy. We plug in 1, 1, we get 2. Plus fv, again, it'll still be at 1, 1, times v sub x. Well, v sub x, y cubed. And if you plug in 1, 1, you get 1. And g sub y at 1, 1, that's our f sub u at 1, 1 times, well, u sub y, x squared. So when we plug in 1, 1, we get 1. Fv at 1, 1 times Now, this is going to be 3xy squared, so this will be 3. Now you say, okay, well that's great, we have 2 equations, but you have 6 things here, Steve, that you haven't marked down. Ha ha ha, you're out of luck, Steve. Or am I? You see, we have one more thing. See, the tangent plane, remember, means to touch, but it also says the tangent plane stores information about derivatives. So, this tangent plane is storing information about these partial derivatives. And where do you find that information? The answer is, you look at the coefficients of x and y. So the coefficient for x, that's the derivative with respect to x at your point. So g sub x at 1, 1 is 7. The coefficient for y is the derivative with respect to y at that point, so that's 1. So now we have 2 equations with 2 unknowns, these partial derivatives, and we do what we often do. We say, okay, well, let's suppose we take the first equation and we minus 2 times the second equation, and we combine. The reason I'm doing minus 2 is I want to cancel something off, so I'm going to cancel off the f sub u's. 7 minus 2 times 1 would give me 5 equals, which, by the way, this is the historical use of the equal sign. If you go back into the ancient text, they used very, very long equal signs. And, okay, they probably also charged a lot of money for those books as well. Okay, so what do we get? We get 2 of these, minus 2 of these is gone. Then we get 1 of these, minus 6, so that's negative 5, FV at 1, 1, which tells us that the derivative with respect to the second slot is negative 1. Well, now that you know the derivative with respect to the second slot is negative 1, you can plug that information back in. Say you plug it in back here. This is negative 1. Then that equals 7, so you can get that 8, because I can move the negative 1 across. It's equal to twice what FU at 1, 1 is. So I get that F sub u, the derivative with respect to the first slot, is 4. Now, we've just put this together. We know the derivative with respect to the first slot, so that's what the f sub x should be. We know the derivative with respect to the second slot, that's what our fy should be. And now we have our information. And therefore, our answer, we write it down, is 4 plus 4 times x minus 1 minus y minus 1, and we leave it in that form. All right. So the next problem. Find the second order Taylor polynomial for f of xy, which is equal to e to the 5x log of 1 plus y at the point 0, 0. That's part A. And part B, suppose that g of xy is a function having second order Taylor polynomial. P of xy equals 5 minus x plus 3y plus 2x squared minus 4xy plus y squared at 1, negative 1. Find the value of g sub x at 1, negative 1. So here, this is a case where part A and part B are independent. They don't have anything to do with each other. So it's like 2 problems for the price of 1. That's a great bargain. So you went into the test thinking, that's just going to be 1 problem. And then you discover it's 2. What a deal! What a deal! Okay, so part A, when you're asked to find the second order Taylor polynomial, the procedure is always the same. You're just going to spend a lot of time taking derivatives. Second order, the word second says you take all derivatives up to order 2. So you start with the derivatives of first order, f sub x. That's not so bad. The 5 comes down. 5 e to the 5x log of 1 plus y. F sub y, that's also not so bad. That's e to the 5x over 1 plus y. Then you do fxx. That's 25 e to the 5x log of 1 plus y. fxy, well, that would be 5 e to the 5x over 1 plus y. And fyy is something. No, it's negative 5 e to the 5x over 1 plus y squared. We know what it is. Come on. Now, after you've done that, you've collected all your second order derivatives, then the next step is you evaluate, because your Taylor polynomial should be a polynomial. So you have to have things that are polynomial-like. These are not polynomials. But the key thing here is that we're getting these coefficients. So we evaluate when y equals 0, 0. X equals 0, y equals 0. That's really easy to evaluate. You get e to the 0 times log of 1. Well, log of 1 is 0. Can't recover from that. When you plug in 0, 0 here, you're going to get 5 e to the 0 times log of 1. Still 0. So that's f sub x. F sub y at 0, 0. Finally, we get something. We get e to the 0 over 1, which is 1. Fxx at 0, 0. Well, 25 times 1 times 0. 0. Fxy. Well, what is that? It's going to be 5 times 1 over 1 plus 0, which is 5. And fxy will be negative 5 times 1 over 1 squared. Negative 5. Oh, yes. The last one is yy. And I screwed up. Yy. There shouldn't be a 5 there. It should just be a negative 1. So I was too happy with bringing the 5 down. So sorry about that, but there we go. Corrected. Check your work. Check your work. All right. Now, you took your second order derivatives. You found all of them. You evaluate all of them. Then the last thing to finish off part A is to say, hey, what do I do? Well, it's a polynomial. So it's the function at your point plus f sub x at your point times x minus a plus f sub y at your point times y minus b plus fxx at your point divided by 2 times x minus a squared plus fxy at your point times x minus a y minus b plus fyy at your point over 2 times y minus b squared. Now, in our case, a and b are 0, so that makes things a little easier. You can actually fit it on your page. And you plug in what you know. So we get 0 plus 0 plus 1 times y, so we get y, plus 0x squared plus 5xy. And then we have a minus 1/2 y squared. And that's the answer for part A. Now, for part B, the key idea here is to say Taylor polynomials store information about derivatives. That's what Taylor polynomials are designed for. They say, hey, I want to store information about derivatives in a compact form as a polynomial. So once you understand that, you say, this polynomial is storing the derivatives up through second order. So in particular, it stores the derivative of the first degree. That's a first order derivative. Now, how does it store it? And the answer is, it's going to have it so the derivative matches. So what we have is that g sub x at 1, negative 1 is going to equal p sub x at 1, negative 1. Now, this only stores the derivative at the point where we're doing the approximation, but that happens to be where we're after our information. We can't say anything else about a partial derivative with respect to x at any other point. Literally, we can't say anything else. But at that point where we have the tangent polynomial, we can. Now, we happen to have p, so we say, well, what is p sub x? So we just start reading it off. Well, that's going to go away. That's minus 1. That goes away. That's 4x. Then this will become minus 4y, and that goes away. So we'll get negative 1 plus 4 minus 4 times negative 1, which simplifies to 7, and we're done with part B. So part B, it's almost really a test of saying, do you understand that concept that second order Taylor polynomials are storing information about your function? Okay, whew. Any questions? Doing good? Hanging in there? There's a question.
So if you were to do p sub x, is it the same thing as just relating p sub xx?
Yeah, if you were to do g sub xx, it would be p sub xx. And the answer is it's going to be a number. it wouldn't be too hard to figure it out. It'd be 4. Okay. So apparently, people love chain rule problems. So I had 2 different emails, 2 different requests. So, ready for another chain rule problem? The problem's so nice, we're going to do it twice. Okay. So suppose we have the function f of xy is g of u of xy, v of xy, and then a whole bunch of information. Wow, that's a lot of information. Determine the tangent plane to f of xy at the point 3, 1. Now, what's the big difference? The big difference here is we don't know what the function u of xy and v of xy is. That's the only difference. The procedure is the same. So we're going to go through this one really quickly. So what do we have? We have g depends on u and v, and u and v are both functions of x and y. I'm after the tangent plane to f of xy, so that says I need to find f at 1, 1, f sub x at 1, 1, and f sub y at 1, 1. Yes? Oh, sorry, 3, 1. 3, 1. I was thinking about a different problem. Okay, thinking about the last one we did. All right, so what do we do? Well, let's do f of 3, 1. Because that one says f of 3, 1, that's g of u 3, 1, and v of 3, 1. So we scan, we say, okay, where do we look? We look f of 3, 1, so we need to find u of 3, 1. That's there. We need to find v of 3, 1, and that's there. 1 and 4. So this is g of 1, 4. And so we scan and say, where is g at 1, 4? Well, it's right there. So it's 1. All right. So that's how we're going to figure out our f value at the point we need. Now, how do we find f sub x? And the answer is we use the tree. So we have f sub x, that's g sub u times u sub x, and then plus g sub v, v sub x. G sub u, u sub x, plus g sub v, v sub x. Every time there's an x downstairs, there's going to be a different part. So f sub x at 3, 1 is g sub u of 3, 1, v of 3, 1, because the insides stay the same. It's like the chain rule for the first semester calculus class. We don't change the insides. The insides stay the same. Then we times it by u sub x at 3, 1. And then we're going to add g sub v, u at 3, 1, v at 3, 1, times v sub x at 3, 1. Now the good news is we actually know some of these values already. We found u of 3, 1 and v of 3, 1. That's 1, 4. So this would be g sub u at 1, 4. And this would be g sub v at 1, 4. So now we scan. G sub u at 1, 4. Well, g sub u at 1, 4 is negative 4. So we get negative 4. How about u sub x at 3, 1? So we go back to u sub x at 3, 1. 7. Then g sub v at 1, 4. That's 7. And then we have v sub x at 3, 1. And v sub x at 3, 1 is 6. So negative 4 times 7 is 28. 7 times 6 is 42. Put those together, we get 14. So that is f sub x. All right, f sub y. Well, same process. So we get that f sub y, g sub u, u sub y, plus g sub v, v sub y. So f sub y at 3, 1 is equal to, and in the interest of space, I'm just going to say it's the same thing that happens here. So it'll become g sub u at 1, 4 times u sub y at 3, 1. You should write it out, but you're going to have so much time. My goodness, 75 minutes. What luxury. Wow. Okay, so that's what we're going to get. Now, what do we get? Well, okay, what is g sub u at 1, 4? Well, the good news is it hasn't changed much since the last time we looked. It's right there. So it's still negative 4. What about u sub y at 3, 1? Well, we scan u sub y at 3, 1. That's 2. So times 2 plus g sub v at 1, 4. So still the same, still 7. That's a terrible parenthesis there. 7. And then v sub y at 3, 1. That's over here, and that is 3. So we're going to get negative 8 plus 21, which makes that 13. So this is 13. And now that you have that information, you get your tangent plane z equals the value of the function, which is 1, plus the derivative with respect to x, 14, times x minus your x coordinate, which is 3, plus derivative with respect to y, 13, times y minus your y coordinate, which is 1. And there you go. Cool. Cool. Now, one thing you'll notice is we don't use very much of the table, which is okay. That's okay. So don't feel like, I didn't use all my data. You don't need it. You don't need it. All right. One other question that there was wanted to know about. Find the limit as xy goes to 0, 0 of xy sine of x squared minus y squared over x to the fourth plus y to the fourth. Now the first thing you should always think about, either write it down or not, at least do it mentally, is you say, well, what's this going to? Because you should always plug in. Because maybe it's something where if you just plug it in, you get an answer. What happens downstairs? Not very promising. What happens upstairs? 0. Ah, good news. What do we get to do? More work. Woohoo! Yes! Because if you see 0 over 0, it means you don't know. However, it makes us very suspicious. Because we know that taking limits, when we get to 2 variables, is a lot harder. So we're going to cross our fingers and say, maybe something simplifies dramatically. And looking at this, that's probably not going to happen because of that sign. So then we say, okay, maybe we can show a limit doesn't exist. So let's go into the mindset, let's try to show it doesn't exist. Maybe we'll get lucky and succeed. How do you show something doesn't exist? Yeah, you go from multiple directions. So you start picking directions. Well, let's suppose we go along, let's say the x-axis. Well, we just pick some direction. And the nice thing is if I'm along the x-axis, I can really say y equals 0. And I only have to look at what x does. So I'm going to say x is going to 0. And when I put in y equals 0, I'm going to get 0 on the top. And I'm going to get x to the fourth on the bottom. But that's really the limit as x goes to 0 of 0, which is 0. I say, okay, now we haven't succeeded yet in showing the limit doesn't exist. We have succeeded in the following. If the limit did exist, it would have to be 0. But we don't know whether or not it exists. So the next thing is to pick another direction. What's another direction we can pick? Y-axis. Now, before we write it down, let's just sort of go into our mind and say, will the y-axis help us? Along the y-axis, what's true? X equals 0, which means that the numerator is going to be 0. Okay, that's not going to give us anything. Let's pick another direction. What's another direction? Y equals x. X squared minus y squared would be what? It would be 0. Sine of 0 is 0, which means the numerator is still 0, which means we're still going to 0. Okay, let's pick another direction. Y equals x squared. Yeah, I'm not going to do that. Well, we tried y equals x. That's going to give us a 0 upstairs. Anything that's 0 constantly upstairs is not going to work. Yeah, we're not going to do that one either. You're trying to be fancy. And I know that's like, I like being fancy. What?
X equals 1.
X equals 1? Well, x equals 1 won't go to 0, 0.
Since there's a sign in the function, can't you bound it and try and squeeze theorem?
Well, we could bound it, but the thing is you only use the squeeze theorem if something is starting to oscillate a lot. If it's not oscillating, you don't need to squeeze it. So squeezing is when you have something behaving badly. And sine of x squared minus y squared, sine is a nice function, and x squared minus y squared isn't blowing up. It's actually going to 0. So this is not a squeeze theorem type question. But you should, if you see like a sine or a cosine and the inside is going, ah! You should be like, okay, we're going to squeeze that and get it under control. Okay, so the reason why people are suggesting y equals x squared or 1 over x or all these other things is they're like, well, there's that one time when we had this crazy curve. And on that crazy curve, we did that x squared. But you don't want to go with the crazy curve if something simpler works. How about y equals 2x? You should always try straight lines, because straight lines are super easy to work with. And another clue that we should probably stick with the straight line is you look at the powers downstairs, and you really want to have something that's compatible. Because they're both 4th degree powers, you say, well, I really want to keep things about the same. So if you have y equals x, it says, well, look, they're about the same order. Whereas if y equals x squared, it says, well, that x squared has a different order in terms of degree of polynomial. And that'll make your denominator unbalanced. It's a little bit harder to work with. So suppose we do y equals 2x. Again, I could do the limit as x goes to 0. Then I'll get x times 2x times sine of x squared minus 2x squared, all over x to the 4th plus 2x to the 4th. Now the good news is that's not automatically 0, but doesn't mean it won't be 0 when we clean it up. So we get 2x squared. Downstairs, 2 to the 4th is 16 plus 1 is 17, so we get 17x to the 4th. Then inside we get sine of, this will be minus 3x squared when you work it out. Now you can pull some stuff out. The minus, because sine is an odd function, I can pull it to the outside. So you get negative 2 over 17. Then I have the limit as x goes to 0. I can cancel off some x squared, so I get an x squared downstairs, and then a sine of 3x squared upstairs. And we say, oh my gosh, that looks a lot like sine of stuff over stuff, which is a really good limit. But it's not quite sine of stuff over stuff. What's missing? We need a 3 downstairs, so we put it there. You're like, you can't just put a 3 there. We can if we put a 3 up here, because then it balances out. Now, what happens to that limit? That goes to 1. So if it's sine of something over something, and if you weren't sure about it, l'hôpital it. Because you've taken Calc 1. You have l'hôpital. Just remember, channel your inner French. Oh, l'hôpital, mon ami! It's been so long! So, the moral is, you get negative 6 over 17. Now, what's true about negative 6 over 17? It's not 0. These don't match. So, limit does not exist. So you should always try straight lines. And if a straight line won't work, then we'll say, casually mention in passing, you may want to consider this curve. Well, that's an interesting suggestion. I wonder why they suggested that. All right, so those were the 5 problems that people had emailed me about. Which means we still have about 12 minutes, give or take. And what do you want to know? Sorry, what? A directional derivative? An implicit derivative. Is there an implicit derivative from the last year? Implicit derivative. Implicit derivative. If I were an implicit derivative, what would I be? I don't think there was an implicit derivative last year. Maybe we're due for one. Maybe we're not. But implicit derivatives are really fairly straightforward. You just make one up. Okay, x cubed e to the z plus z cosine y squared plus 2x equals 2, and then you hum and you ha for a second, and then you finally say 0. Okay, and then you want to find what is partial. Well, what do you want to have the variable on the top be? Z? What do you want the variable on the bottom to be? Well, the reason I'm asking No. Okay, partial z, partial y. Okay, so implicit derivatives say I cannot solve for z. In fact, you can't. You can't. You know, there's the problem is there's a z upstairs, and inside the exponential function there's a z outside the exponential function. But you can't get z by itself, as much as you'd like to. So we say, okay, we can't get z by itself. So how do we take the derivative of z with respect to y? Well, the answer is we think of z and say, even though I can't do it, I'm going to pretend like I can. So when we stare at this problem and we're thinking implicit derivatives, what we do is we say, the way to think about this is whenever I see a z, I really think of it as a function of x and y. So that this is my real expression here. So it's x cubed times e to the z to the power xy plus z times x of xy cosine y squared plus 2x equals 0. Now this is, again, this is what we're thinking. So we're in the test. We're like, this test is going great. And here's my thought on this particular problem. And it's, you know, maybe we're smiling. That's too happy, but okay. All right. But anyways, we're having a good time on the test, and that's what we're thinking. We don't write it down, but that's what we think. And now that we have this beautiful thought, what we do is we take the derivative of everything with respect to y, and the reason it's with respect to y is we look down here. That's where you see where you're taking the derivative with respect to. So we go through and we say, okay, when I come to my first term, you know, up here it looks like there's no y, but we know that there is a y because we thought about it. So that's going to be x cubed times e to the z times the derivative of z with respect to y. Now the question is, how do we write the derivative of z with respect to y? The answer is we write the derivative of z with respect to y. Plus, now we come to our next term, and now we see there's actually two y's, not just one, but two. So we have to do the product rule. Derivative of z with respect to y, derivative of the first, times the second, plus z, which is the first, times the derivative of the second, which will be minus 2y sine of y squared. Then we go to our last term, and we say, nope, there's not even any y to begin with, so this all equals 0. Now, from here, all that's left is you say, let's take all the terms with the partial z, partial y, and we factor that out. That's x cubed e to the z plus cosine of y squared. And then everything without a partial z, partial y, you move to the other side. So you get 2yz sine of y squared. And finally, you divide through, and you get your answer. Full points. On to the next one. All right, so that's it. So implicit differentiation, just remember, whatever variable you're taking, function of derivative of z with respect to y, make sure you say z depends on y, and then take the derivative of everything with respect to y, and life is good. Okay, other questions? We still have time. All right, then maybe we'll do a speed run through the exams. Okay. 5 minutes. We'll talk about the problems until we run out of time. So this problem, f of xy is something. And it says find all the critical points. Now, whenever you see something that says find the critical points, the process is the same. You look for where does the gradient of f equal 0. Now, theoretically, there's the chance that the gradient is undefined, but in practice, we've never been able to come up with a good one. So you set gradient of f equals 0, which means you get f sub x equals 0, f sub y equals 0, 2 equations, 2 unknowns, and you solve. So look for things like factoring. See if you can factor one of the terms. That's better. If you can't, look for substitution. And if you can't do that, check your derivatives, because you're going to be able to do that. All right? You're not going to come up with like, oh my gosh, I have to solve a 5th degree polynomial. That's wrong. You've made a mistake. Recheck your work. Then there's a classify, and for that one, remember that says you look for D. So make sure you write down what d is, fxx fyy minus fxy squared. Be careful when taking these derivatives. You evaluate d, and then if it's negative, you get a saddle, and you write it down. If it's positive, and you say, okay, look at fxx or fyy. If it's positive, then you're at a min. If the fxx or fyy, they'll both have the same sign. If it's negative, you're at a max. And if d equals 0, just say inconclusive. Or if you can't spell the word inconclusive, just say, we don't know. You don't actually have to keep going. Okay, so that's if you see a find and classify, that's what you do. For limits, we've talked about limits. So there's a couple strategies. Sometimes you can say, plug in and see what happens. Now, if you plug in 0, 0, you don't get 0 downstairs, life is good. So plug in, that should always be your first thing. If you get an answer, you're done. We mentioned this before. We talked about what happens if you have something bad on the inside. So log, this is getting close to log of 0, that's blowing up, but it's inside the sign, so it's wildly oscillating, so this would be a squeeze. So there's only a couple things you look for. Either you plug something in, you squeeze it, or you approach in different directions. So sketch the domain for the function below, and you want to shade the interior of the region. So what do you look for? Well, you look for a couple basic things. You want to avoid divide by 0, square root of a negative, and a natural log of something that's less than or equal to 0. So what you do is you go through and you figure out what those things are. Now, if we ask you to sketch, we'll give you something to sketch with. But we'll also give you things that you can actually sketch. We're not going to be like, sketch x to the 5th e to the x plus 17 cosine y. You know, that's not going to, it's going to be like a circle or a straight line or a parabola. In this case, it turned out to be y equals 1 over x. They're going to be functions you know. So don't panic too much about sketching. By the way, make sure if you need to shade something, you shade it. So this one says you shade. So maybe your region turned out to be something like this. Again, this is not the answer, but maybe it turned out to be that. So you should shade the inside. There are other times when we ask you to sketch, and based on the speed I'm going at, we're not going to get to the other one, where it says sketch a level curve. And we had people who would sketch level curves, and then they'd start shading stuff in, and we'd be like, what the heck? You don't shade for level curves. So make sure you know what you're drawing, and don't just be like, oh, there was that one time I drew a picture and I had to shade. No, no, no. We're not always going to make you shade stuff. So this problem is somewhat infamous because it sounds complicated. You're hiking in the 3D forest, and you've got furlongs and all these other things. But this is what you do, is you say, okay, look, let me try to strip away all the stuff that's confusing to me, and I'll figure it out. This says the stream flows in a particular direction, and it's dropping at a rate of 15 cubits per furlong. So how does water flow? Which way does water go? It goes down. And it goes down as fast as possible. So when you talk about water flowing, see, water, it took multivariable calculus a long time ago. It took it when it was first offered. And it said, I know how to find the way to go down as fast as possible. So this is a gradient problem. And what's happening here is they're giving you information about your gradient. And you reconstruct your gradient. And once you know your gradient, now you can say, well, this is saying go in a different direction, so it's a directional derivative problem. And for directional derivative problems, you remember it's the gradient dot a unit vector. Okay. So suppose you have this crazy function, and you want a tangent plane, which is also to the level surface. Sometimes we call these implicit surfaces. Sometimes we call them level surfaces. This is the shove everything to one side. And so here's the everything. And then you take the gradient of f at your point, 0, 1. The thing that makes this problem interesting is you don't know z, but you can figure out what z has to be. It pops out that z has to be, I don't know, 3, I think. But that's your normal, and then life is good. So Kelly is in the business of producing widgets and gadgets, and you have this function here. Each gadget costs $2, each widget costs $1, and you spent money on production. How many widgets and gadgets should be produced to maximize profit? Well, you have the profit function, you have the cost function. So at any rate, what is this? It's a constraint. Because you say, look, I have $300, I have things that cost money to produce, I can figure out how many I can produce, this is how much profit I get. So whenever you have a problem which has an optimization with a constraint, what's your technique? Lagrange multiplier. So look for optimization with constraint, you're ready to go. Do I want to keep going or should I stop? Keep going for another minute or two? Okay. Find the directional derivative of this point at the point 2, 1 in the same direction as the vector negative 4, 3. Now what's wrong with this vector? Not a unit. Make it unit. So take negative 4, 3 and divide by the magnitude of negative 4, 3. And now, remember, you just find the gradient of h at 2, 1. Once you have these two pieces, you dot them. That's the directional derivative. Life is good. Directional derivatives are pretty easy to find. This is one of these sketch problems. This one's fun. It turns out that you get something that looks sort of like an 8 here, but the origin is missing. And this one is actually one we did before in class. And it says, does the limit as you approach 0 exist? Because you should actually label these. This is 2, this is negative 1. And what happens is, as you approach along this circle, you think the origin should be 2. As you approach along that circle, it's negative 1. So it doesn't exist. But okay, but be ready to sketch the level curve. So if you see anything like level curves, what does that mean? You set the function, level curves is set the function equal to like the number. So it's 2. And then you say, okay, this is a curve in the xy plane, and you sketch it. Find the tangent plane to the surface. So this is, take a gradient, find a tangent plane. And then you see the word estimate. Now, whenever you see the word estimate on this test, you might also see it associated with the word linearization or okay. They'll have spell checkers, so they know how to spell linearization. So linearization is a fancy way of saying tangent plane. So whenever you see a word estimate, that just means use the tangent plane. So whenever you see that, just your idea is use your tangent plane. If you use the tangent plane, life is good. And okay, so that's what we have to say about that one. This is another classification. Take your partial derivatives, set them equal to 0. Absolute max and min. How do you know how to recognize an absolute max and min problem? The answer is, look for the words absolute max and min. That's a dead giveaway. So the absolute max and min is you always make a list. Make sure you include your corners. Make sure you check the interior. How do you check the interior? Gradient equals 0. And then you check your boundary one at a time. So you check each side. So they're going to have three parts for this picture. And after you've made your list, you plug it in. And whichever is the largest, that's your max. Whatever is the smallest, and that's your min. No second partials test. Just make a list, plug it in. Largest is the max, smallest is the min. And the last one is, we've already done problems like that. So that's it. Good luck.